to study how to reduce the power consumption, right? We're done with the logic. How do we reduce the power consumption, right? We can actually, there are a few things that we can do. One is use alternative architecture. For example, use carry look ahead instead of ripple carry. Another is do the parallelism pipelining, okay? So there are two things. One is called throughput, one is called latency. Can you tell me what is the difference between throughput and latency? Anyone? This is very important. If you don't understand this, you definitely understand the concept, but you need to understand the term, the name, right? What are the difference between throughput and latency? I thought you were trying to answer, Omid.
I was gonna guess.
Yeah, please.
I was gonna say like throughput is like how much bits, and then latency would be like the time.
Almost.
Delay. Okay.
Throughput is number per unit time. Okay. So let's say we are in a factory. You need to make some toys, right? It's okay, you do it super slow. As long as you have 1,000, 10,000 workers working at the same time, your throughput will be high because per unit time, your factory dump a lot of toys out of the factory. That is the throughput. So for example, my DRAM is low, the connection, one bus, maybe it's 100 megahertz. But if I can design my DRAM so that it has 10 buses, then what is the throughput? It becomes 1 gigahertz. Okay, so yes, it is low, but the throughput is high. Is this useful? Yes. For example, if I want to copy a huge amount of data, let's say a lot of picture, I have 10 gigabytes of picture that I need to copy from this computer, from the memory or to my CPU, right? For example, you are doing machine learning. While you are slow, yes, your speed is only 100 megahertz, 100 megabits per second. But because you have 10 buses, I can get 1 gigabit per second. That is good enough. Then we care about throughput. But latency is different. Latency is something that we want to respond immediately. That is the time to get data. Get one piece of data, right? For example, I am reading the code. I just waiting your memory to tell me what I should do next. Even there is a very small instruction set, right? Even you have a very high throughput, but the latency, if it is low, then it's not useful to me because I still need to wait for 1 second in order to get the decision, right? So in some operation, we care about the latency. In some operation, we care about throughput, right? So if we want to reduce the power, right, so that we can reduce the supply voltage, it's going to make things very slow. However, in some applications, if we only care about throughput, for example, I want you to calculate 1 gigabyte of data of addition and then comparison. Well, as long as your throughput is high, then that is good for me, right? But if I actually care about latency, I only want you to get 1 addition, then even you have high throughput, that is not enough. We care about the latency. Okay, so let's look at an example. Here we try to do addition A plus B, and then compare to C to see which one is larger. I don't know if this pseudocode makes sense. How about this? Right, this is the question that we try to compute. A plus B, and is it larger than C? Okay, now if I try to do it all at the same time, this is the register. We are going to learn it in very soon, right? I need to complete the calculation within T period, right? Because here I go to another register, right? So from here to here, you need to finish in T, right? Within T second, you need to finish this computation. And because of this, then I can clock my frequency at 1/T. For example, if this is, let's say 1/T, right? For example, the frequency equal to 1 gigahertz, then T equal to 1 nanosecond. You need to finish this calculation in 1 nanosecond. But let's say I don't care about the full latency, right? This is the latency. Right? If I don't care about latency, I just say that within today, you need to finish all this computation. Then what I can do is reduce the clock. Now this one becomes 500 megahertz. Okay. When this is 500 megahertz, can you tell me what is the latency here? When it was 1 gigahertz, the latency is 1 nanosecond. And now it's 500 megahertz. What is the latency? Then I will get the answer. No one, it will just be double, right? It will be 2 nanoseconds, right? I take double time to get the answer. Okay, but why do I this? Because I reduce the VDD. So I can I reduce VDD, I save the power, but I need to go to a lower clock. But however, I duplicate. Do you see that? I duplicate the hardware. And I will select them at a higher rate. When you are done, I select this one, then I select the other one. The throughput is still 1 per nanosecond, right? Here, the throughput is also 1 per nanosecond. Yeah, every 1 nanosecond, I get 1 data computer. Here also, every 1 nanosecond, I get 1 data computer. But indeed, it takes 2 nanoseconds for each of them. Is this okay? Any questions? So we can look at some example, right? For example, we know that P equals to, let's say, C ref times V ref square times F ref. This is the power consumption if it had before, right? So now before, for example, the T might be 22.5 nanosecond at 5 volts VDD, okay, with capacitor equal to 1. Now we change to this parallelism and pipelining. T may becomes 5 nanosecond by reducing the voltage to 2.5. Of course, we have more hardware. The capacitance can be 2.15. Okay, if you do a calculation, the new power consumption is 0.36 times of the old one. Okay, but however, yeah, this is good, right? Because we only care about throughput in this case. So we have lower power consumption, we have the same throughput, but remember, area is 3.4 times larger. Right? Do not think that it's just 2 times larger. You have a lot of overhead. Okay, so this is one way to reduce your power consumption. by reducing the voltage. But with reducing voltage, you hurt the performance. So what you can do is use parallelism or pipelining. Any questions? If no, then let's continue to see how we can further reduce the supply voltage without affecting the effect, without affecting the performance. Here it shows that, hey, I can have multi-supply voltage. Why? For the fast path, the path that work very fast, I can reduce the supply, right? Because, for example, if you look at this one, right, I highlighted the gray logic has low power supply because they are fast, right? So, but the white one, I put them, I apply a nominal VDD, right? Because they are the critical path. That's why, which one is the critical path? The white one is the critical path. We need to make sure this one finish within the time we want. While this guy always waiting for this one, why do I want to supply a high bias, right? So I will apply a lower bias, lower voltage for the fast path. Then I can reduce the speed, right? How about let's think in this way. You drive an old car. Your father drives a Ferrari, right? His car is much faster. And you guys want to reach at the same place to meet your mom for lunch. And why he want to use all the fuel with very low efficiency to reach there and wait for you if you are so slow, right? So he can go to a power saving mode maybe for his car, so that as long as he's a little bit faster than you, then all of you can have lunch at the same time. Right? So for your car, you definitely need to use a lot of energy to go as fast as possible. For his, he can really save the energy. That is the idea for multi-supply, right? Another thing is, if you, in your design, if you have something have large capacitor, because the power consumption is related to CV squared times F, then you should really reduce the voltage at those parts that has large capacitance. Okay, so you don't reduce everywhere. You reduce where you gain the most. Right? But then what is the problem? Right? You might have a multi-level voltage. The problem is, for example, here, I have a data path. This is slow, 10 nanoseconds. And then I have control path. This is fast, 5 nanoseconds. They run in parallel, right? So what would I do, right? I will reduce it. For example, I just make the 4 nanosecond to 10 nanosecond by reducing the VDD from 2.5, let's say, for example, to 1 volt. Okay, then you will get a lot of reduction in energy. But your speed is still the same. It is not compromise, right? The only problem is you are talking to each other. This one is using 1 volt. This is 1 volt VDD, but this is 2.5 volts, right? So, am I able to talk to the other? Actually, this can be very dangerous. For example, let's think about an inverter. This is 2.5 volt. And then you only come with a 1 volt VDD. You cannot turn this off, right? You turn this on, but cannot turn PMOS off. Although your input logic is 1, you expect the output to be 0, but you cannot turn this off. This cannot be 0, right? So what will you do? You will use this type of couple logic. So although this one come in, right? I want to be an inverter, but this one come in as 1 volt. So this one is turned on. When this is turned on, it will drive this to 0, right? This is 1, and then this becomes 0. When this is 0, then this is on, right? Because this is on, then you will drive this to 2.5. And when this is 2.5, then this will become off. And then you don't have this leakage problem. So this is a method to avoid that. Then it means that you need to be careful when you are doing multi-VT situation. Okay, now, so what is the scenario we want? We have many different paths, right? So before we have the single VDD, we have a distribution like this. A lot of them really finish it very fast before the clock. So if we use dual supply, we actually increase the delay of the fast circuit, but we never exceed the target because this target determines your clock. The slowest one, we cannot make them slower, right? So we have this distribution. Okay, any questions? So we have learned to reduce the power supply, but without adding performance by doing parallelism, and then only apply them to the fast logic, but we need to be careful about interfacing them, right? We can even have a multiple threshold voltage for different transistors. Okay, in this case, you don't need to do any conversion because you have the same VTT, same VDD. The difference is VDD minus VTH is different because you have different VDD minus VTH, right? And just remember, I on is proportional to VDD minus VTH. You do make it slower, okay? But I off, right, is proportional to exponential VDD, which you apply over let me just call it KT over Q. Okay, so it is much lower. Okay, so by doing this, you actually can reduce the power supply up to 90%, right? For those not in critical path. These are in critical path, low VTH. The gray one are the low VTH. So this is the critical path, like what I mentioned earlier, right? So they run very fast. So this time we don't slow down anyone. We just make the critical path, those running slow, faster, right? But then we can reduce VDD, and as a result, you still meet the timing constraint, but you have a much lower power consumption. Make sense? Any questions? Okay. Now then, another way we can do is to reduce the switch capacitor, right? First of all, think about the transistor sizing. Do you still remember how to size the inverter? We have inverter like this, right? Ideally, we say the delay equals to TP0 times 1 plus F divided by gamma for inverter, right? Each stage has the same F. Okay, and what else? Then it means same delay, right? So the size get larger and larger, but if you recall, the delay is the same. If I have 10 stages, each of them contribute 1/10 of the delay. And now I say hey, turn out that we don't need to have such a fast inverter train. You can make it slower. Can you make it slower, a little bit slower, but at the same time reduce the power consumption? So in this case, which one would you reduce? They all have the same delay. Delay is the same, right? So I can choose to reduce either, right? So this is T1, T2, T3, T4, right? We say T1 equal T2 equal T3 equal T4, right? Right? If I have budget to increase one of them, which one should I increase? Let's say now the total there T1 plus T2 plus T3 plus T4. I have a budget to have a delta. Where should I put the delta? Should I put it to increase the first stage? So it is T1 plus delta, T2 plus delta, T3 plus delta, or T4 plus delta? Right. I already give you the answer. I will, right? I will increase T4. To T4 plus delta. Why is that? I give you some hints already here. Anyone? Yes, everyone is prepared for the master submission, project submission. Okay, that is because the last stage has the largest capacitance, right? And we know that power consumption is proportional to CV squared. If I can reduce the delay of the last stage, then it will reduce the total consumption a lot because the last stage has the largest capacitance. Make sense? Right? So basically, it is the same. This is a simple inverter chain. Same for other thing. You want to optimize the stage that has the largest energy consumption. So same in your project, right? If you want to improve the energy consumption, think about which stage has the largest energy consumption. And usually it is the one that is driving, has the largest capacitive load. Any questions? Okay, if no, then let's continue to see how we can improve the power efficiency, right? Of course, we can do it through by reducing the activity, right? If your CPU is not doing any computation, that is the best, is not consuming any energy, right? But there are some activity that we can save, just like at home. If you need to go downstairs to get something, get it all at the same time and come up. Why you want to go down to get a cup and then realize I did not fill up the water, then go down and fill up the water and come up, oh, realize that I actually forgot to add ice and go down one more time and then to add the ice and come up and realize that I forgot to get the cake, something like that. You can do all the things at the same time and then go downstairs and come up, right? So similarly, there are many activities that we can do in the CPU to reduce the power consumption. One of them is avoid resources sharing. That is interesting. For example, let's say I have a counter, right? Let's say for some reason, it always runs, very extreme case, it always give 1. And another counter always, this is just extreme case, give 0. Any switching activity here? Do I have any switching activities? No, right? No switching activity. So no power consumption. Let's say I try to save the area, right? I try to have the share bus. So I have a multiplexer here. What will be the output? It's going to be 0, 1, 0, 1, 0, 1, 0, 1, right? Because I first need to sample counter 1, I get 0, get 1. Then sample counter 2, I get 0. So although they are constant, then I always have this switching. That actually has a maximum switching, right? Which consume a lot of power. Right? So this is a more realistic one, right? You do have some switching. It's not always 1, always 0. If don't share the bus, this is the activity that you have. If you share the bus, you see the output changes a lot. And as a result, you have more power consumption. So when power consumption is important, for example, you design some handheld device, some chip, low power chip, then you need to rethink whether I should try to save the area or I should reduce the power consumption, right? Another example is here. This is added. We see something similar, but this is more dramatic, right? I start with 0. So what is 0 plus 0, right? The carry in is 0, and then everything is 0. Of course, output is 0, right? And then I have a number comes in, carry in become 1, and everything become 1. What should be the answer? Well, 1 plus 1 equal to 0. So I propagate 1. And then 1 plus, and then 0, right? The other B is still 0, right? You just keep propagating, eventually becomes 1, correct? So there should be no switching. So I expect that my power consumption should be very low, right? But unfortunately, because of the delay, yeah, you have 1, okay? This is 1, I get 0. But it takes time to know this carry is 1. And I should also write it down that before that, right? Before the switching, this is 0, right? Because everything is 0. But before the 1 comes in, this is still 0, and you give me 1. So I will try to evaluate 1 until later you tell me, no, this is actually 0. Then I go back. For 3, it comes even later. Then I already switched to 1, and then later you tell me to stop. For the last bit, you see that? This one already get 1. And you wait for this one to propagate all the way to here, and eventually you realize that it is 0. So here consume a lot of energy, where I expect that there should be no energy consumption except the last carry out, right? So this is because of the path unbalancing. So you want to balance the path. So what you can do is use something like carry look ahead, a 3 carry look ahead, or a multiplier that we learned earlier. That can reduce this type of activity. So ripple carrier is not just the area and delay has problem, not just the delay has problem. It is also the power consumption, right? So definitely you don't want to use ripple carrier for your project. Okay, any questions? Let's see. Okay, now then something more fancier, right? Just now we say we can have a threshold voltage that is different for different transistor, or have voltage supply different for different block, right? We can also use something called dynamic voltage scaling. Right? So this is, for example, when you are playing video, or in your cell phone, sometimes you're doing some very high throughput computation, computational intensive software. Sometimes it's just reading the text. You don't need much CPU power, right? So if you can slow down your CPU when you're just reading the text, that can extend the battery time a lot, right? But how do you know that? This has to go from the software level. Your operating system tell you that, hey, now we are relaxing, reduce the clock, so we save the battery. So this is not even up to the level of co-optimization with software. Although it was not mentioned in the textbook, but it was just what we have nowadays, the very important concept. We co-optimize everything, right? So here shows that if you reduce the power supply, your energy consumption per operation really reduce. But it also means that you are very slow, right? And here also show the same thing. When you reduce the power supply, the maximum clock frequency will reduce, right? You're slower, but you really reduce the power consumption. Okay, so how do we do that? So basically, in any chip, right, we can duplicate a ring oscillator here in the chip. So here represents the typical delay in the chip. Okay, so this is just a dummy ring oscillator. It's not useful. It's not for any computation. Okay, but it oscillates, so you give a frequency. Right, so you fool the counter, do some sampling, and then you compare with the desired frequency by the operating system. Operating system realize that now I'm only running the test editor. I can be very slow. I don't need to run in the turbo mode. Then you say, reduce your frequency. Then they compare the frequency. Based on that, they are going to change this transistor and the control so that the threshold, the VDD is going to be smaller. So you're running at lower frequency. And then you will compare. Is it the same? Or you miss the target, lower frequency, then you will just keep it, right? If you're too low, then you will ask you to increase the VDD, right? So based on what the operating system want, right? I'm doing the the video encoding, then it might ask for higher frequency. But the main point here is that it's very common in any chip design. We will add a dummy, not really called dummy, but just a replicate to detect what happened in other parts of the circuit, not just for the frequency, operating frequency, right? But also for the degradation, but also reflected in this ring oscillator. Because as the time goes by, your device will degrade, their frequency, their current will become smaller. Then we hope that we can gauge how bad they are through this one. And then we do something from the operating system to make it stable. Okay. Any questions regarding to this topic? If no, then we go to the last slide of today's topic. It is just now is the dynamic VDD, right? Threshold voltage, right? We do it dynamically. At the same time, we can do the threshold body bias dynamically, right? So if you remember the VTH of a transistor equal to their VTH 0 plus gamma times square root 2 phi, right? Minus VBS minus 2 phi. I think I swap it. Right. if let me swap it back. Right. If I can forward bias it, anyone can tell me if I forward bias it, forward bias the junction, right? Forward bias the body, what will happen to the threshold voltage? Is it increase or decrease? Okay, you will decrease, right? What happened to you guys today? No one respond to me, right? For example, forward bias, body to source, right? Then VTH will reduce. Then we can operate at higher speed, right? So that is the idea. But how do I detect it? I have this type of control circuit. Okay, so I won't show the detail, but this is like this, right? If let's say VB increase, the body bias increase. Okay, when body bias increase, then of course we are going to increase this one, right? Because this is connected to this one. And because of this, the current, the VTH reduce. Okay, because it's forward bias. When VTH reduce, then the I increase, right? If I increase, then it means this part is going to reduce, right? Just an inverter. So when this part reduce, you basically reduce this one. It means making this one to have a higher current. So this one will increase the control. This is 5 actually, right? Because the VGS increase, right? So this one will charge up. Charge up means what? It means that, hey, pump more. So when you pump more, then the volt potential here will decrease, right? So that will have a negative feedback. So based on how much leakage is here, we can adjust it dynamically on the threshold voltage, right? If the leakage is too much, then we will just reduce the reduce this body bias. Okay. Okay, so that's all I have for today. Any questions? If no, you can leave now.